תודה לכולכם שבאתם, וברשותכם אעבור לאנגלית. Thank you everyone for coming here tonight. It's lovely to see you here, coming to hear about such an interesting and intriguing topic. This public lecture is organized by the Astrophysics Research Center of the Open University, and it is also sponsored by the Israel Space Agency as part of the activities of the Space Week, which is kind of nearing its end this week. So it is an honor and pleasure to welcome our speaker tonight, Professor Rog'er Blandford of Stanford University, where he is a Luke Blossom Professor in the School of Humanities and Sciences, and he's also a Professor of Physics, Particle Physics, and Astrophysics at the Kavli Institute for Particle Astrophysics and Cosmology. Rog'er did his PhD in Cambridge University with Martin Rees, who then went on to become the Astronomer Royal and then the President of the Royal Society. He then continued with a research fellowship at Cambridge, during which period he also visited the US, the Institute for Advanced Study in Princeton and Berkeley, and did some of his famous works already at such an early stage of his career. He then took a faculty position in the California Institute of Technology, Caltech, where he eventually became Richard Chase Tolman Professor in Theoretical Astrophysics, where the previous chair of that endowed professorship was Richard Feynman. So this can give you an example of his stature in the field. In 2003, Professor Blandford moved to Stanford to be the founding director of the Kavli Institute for Particle Astrophysics and Cosmology. And on a more personal note, 1 year later, I did my second postdoc there while he was the director. So I know him for quite a number of years now. Rog'er Blandford has won numerous prizes and awards. I can't possibly mention all of them here. I'll just mention a few, which are the Eddington Medal, Gold Medal of the Royal Astronomical Society, and more recently the Shaw Prize in Astronomy. Rog'er is a very well-known and respected astrophysicist and cosmologist. One important testament of this is that he chaired the US National Research Council Astro 2010 Decadal Survey. And he is particularly well known for his contributions to the study of black holes, and in particular supermassive black holes at the centers of galaxies, about which he will talk today. Rog'er has also greatly contributed to public outreach, and he's involved in educational initiatives to improve the knowledge and involvement of the general public in scientific issues. And he's given many public lectures in astrophysics and cosmology. So with no further ado, let me welcome our speaker tonight, Professor Rog'er Blandford.
Well, thank you very much, Yoni, and it's a great pleasure to see you again and to see all of you and to be back in Israel. This is my third visit to Israel, and it has been a very exciting time scientifically. It has also been personally nice, seeing many old friends and colleagues. So I'm having a really great time, and I shall be very sad to leave in a couple of days' time. But so thank you very much for a very warm welcome everyone has given me here. And the Space Week was a lot of fun. It was a very positive experience seeing it and listening to some of the talks and so on. And then there was a black hole conference there on the second day, which Yoni and I participated in. And again, I learned a huge amount from it. I thought I'd heard all these things before, but there was a lot that was new there, and it was a very exciting experience for me. So this has been a great week. So thank you very much, everyone. Now, what I'm, as Yoni said, what I'm going to talk about is massive black holes. These are the ones that are found most in the centers of galaxies. And I'm going to give a slightly personal perspective on these and try and, in some sense, perhaps maybe even, I won't say humanize them, that's a little bit of a stretch, but I'm going to try and say that they're a little bit, there's much more going on than might be apparent to casual readers of the popular press. And so let me go on perhaps to the first slide. They've of course been a lot in the news for many, many reasons. Here's just some of them here. There were in recent years 2 Nobel Prizes that were awarded to friends and colleagues of mine. Now let's see if we, there's a red pointer there. Is that visible from the back, or should I? You can see it, excellent, okay, because it doesn't always work. Okay, so this of course was for the discovery of gravitational radiation. Irena Weiss and Barry Barish and Kip Thorne here, and then on the right-hand side was for the, well, actually for 2 things. One is Roger Penrose here for his theoretical work on black holes, and then Rainer Genzel and Andrea Ghez for their observational work looking at the particular black hole at the center of our galaxy and tracing stars around them using infrared astronomy. And these are all remarkable and different accomplishments, truly remarkable accomplishments that represented the work of a very much larger community. But the fact that this was recognized means that black holes really have become very famous. So here's a sort of cartoon, I'll show a little bit more about this, of 2 black holes merging and making gravitational radiation, which was seen, and it was a very very big deal when that happened. And then finding about the properties of galaxies, and this is perhaps a little bit closer to the topic I have here, the stars that are orbiting around the black hole in our galactic center. And I must admit, when I saw these pictures with all the hoopla about the Nobel Prizes, I thought back to this one when I saw this one, which came later. And for those of you who know about the history of the physics of black holes, my first reaction was, well, maybe black holes have hair after all. So now also on top of this is, whoops, what happened then? There we go. Okay, after this was the, after the work was done, was the famous Event Horizon Telescope of the gas orbiting the massive black hole in the center of the galaxy known as M87. I'll say a lot more about that. And this image was become iconic. I think the director of the National Science Foundation in the United States told me that this was the most downloaded image they'd ever had from their website. And of course, everyone has seen this. And so that also gave prominence to black holes. But they're also scientifically, and I'll say more about this, they're also associated with the frontiers of astrophysics, And I'm thinking about the sort of extremes, going to the limit of what you can do and see. And there are the very highest energy gamma rays. These are photons that have the very highest energy. The very highest energy neutrinos. These are sort of shadowy particles. We'll say a little bit more about that. And the various highest energy cosmic rays. These are really high energy. So high energy, very high energy. That's typically about 100 times more. And then ultra high energy. We're running out of superlatives. That's 100,000 times more than these. So, we're getting really up there. If you take the ultra high energy cosmic rays, their energy is about that of a well-hit tennis ball, for example. Okay, so it's, this is remarkable. So, now, there has been some skepticism, I would say. Here's a cartoon. Here's a picture of a black hole and so on. Here's another, I show you another example here. When I first saw this, sorry, I'm getting away from the... Oh, I take choose. Okay, I'll try and remember this. This requires two-fisted coordination. I'll do my best. Okay, when I showed this image here to my colleague and current collaborator, Noemi Globus, who's an Israeli and working now in the United States, her first reaction was to say, oh no, don't trust it. So this is what it really is. So she sent me this back in about 10 minutes. It's all one of these government cover-ups, and so that's what it really is. So anyway, there you go. And of course, sort of more generally, one's fighting against a certain amount of bad press for... I'm here to promote black holes, not to give them bad press, but this is something you have to... Any young people here are looking for an opportunity for a career, being a scientific cartoonist. There's a lot of opportunity there, as you can see. The standards are low. Okay, so they appear in the finest literature. I can't resist calling this pulp fiction. And here the casualty may be the English language, or indeed the translations. And I apologize for speaking in English. My Hebrew is non-existent, and this would not go far, I can assure you. So there's all of this stuff out there, for example. And of course, historically, I won't say that Dante anticipated the black hole, but he certainly had something similar in mind. This is Botticelli, of course, and economists and politicians have not been slow in invoking them pejoratively and not favorably when they wish to score some political point. I'm sure that such a thing could never happen in Israel. And then, of course, in the movies, there have been several movies, and here the casualties may have been to the careers of otherwise promising actors. The first one on the left-hand side got some ideas right, but then threw in gravity-free zones, an evil genius, mechanical slaves, extrasensory perception, and Anthony Perkins. It introduced some sort of impressionistic stabs at the science, but ended with the heroes going into the black hole and then contriving a happy ending. The second was quite explicit about the idea of an event horizon, which I suspect everyone has heard about, this sort of one-way membrane around a black hole. And this is, if you like, a point of no return from which no one, not even a superhero, can escape. But then it got into white holes, which are time-reversed black holes. In this case, they made no shame about the incipient violence of black holes, and it was mediated by actors who wandered off into a slasher movie. The critics were not kind to this one. So you should have got the idea, if this is your only exposure, that black holes are a particularly bad thing. Here's something that was much more sensible from the movies in some sense. The first was based on a novel by Carl Sagan, and one of my students, well, one of my colleagues, Kip Thorne actually, and also a student of mine, were engaged in this as advisors, and it was much more creative. It depicted radio astronomy in a fairly serious way, but it also explored some other ideas, including wormholes, which are generalizations of black holes that in principle allow time travel. So unlike the screenwriters of this movie, who sort of created a sort of interstellar metro system, where you could go from here to there in a sort of almost unconstrained way, my own opinion is that wormholes, at least of this sort, the level at which you or I could, get on board, don't exist. I can't actually prove it. But wormholes are a great gift to Hollywood screenwriters, because once you have written yourself into a corner from which there is no literary escape, then you can invoke a wormhole and start again. And that happens in more than one of these movies. So maybe wormholes do exist after all, but my advice to you is don't bank on it. So there you are. Okay. So anyway, so what have we got now? Okay, yes. Now I mentioned Kip Thorne, who's my colleague, and he was the sort of the originator, the only begetter, if you like, of Interstellar, which was this famous and very successful movie. It went through many transformations, and it was a pedagogic, in many respects, it was a pedagogic demonstration of much of the weird physics that really should happen around black holes, and especially involving relativity, and the ideas that you will age at different rates, depending on the gravity and so on. That sort of idea is brought out rather graphically here. A sort of very human story, a father-daughter relationship. So there's the father and there's the daughter. Go figure. And there was lots of desert to which Israelis can relate, bad crops, which to many other people can relate, and fancy graphics and some creative space engineering. And in fact, Kip Thorne had to write a book to go alongside the movie as a sort of guide to the physics that goes alongside it. And so, where are we? There we go. At the same time, the reason why I had a sort of, I was able to witness this thing from a safe distance, that he and I were writing a textbook on modern classical physics at that time. It has 1,600 pages and 3,000 equations. And Kip has very graciously signed over the movie rights to me. And so I'm still waiting for a top-line producer to take this on, but you never know. Who knows? Anyway, I've not been to. It's not so good. So my job now is to get you enthused about black holes, having said all these introductory remarks. So let's go on to that one. Okay, so I'm going to start by telling you about gravity, and this is in a cartoonish way. This is Woolsthorpe Manor in Lincolnshire in England, and it is where Isaac Newton was born. And those of you who know about mathematics will recognize this immediately because of the integral signs that are carved into the wall here. This is a well-known construction from that device used at that time. Now, this, of course, is a cruel thing that I said, because the integral sign was introduced by Leibniz, who was Newton's great rival. And so at the time, and so I was actually born within 5 miles of Woolsthorpe, and I've always boasted about this to my students. They are totally unimpressed. What has that got to do with anything, they say? So, but at any rate, I remember this. But Anyway, but here, of course, is the famous apple, and I'm sure it's exactly the same apple tree. And this is all just a metaphor. It's like Galileo and all of that. But it's, there is a real point there, because Newton recognized that he introduced the force of gravity, which was introducing a force which went beyond just the kinematics and saying things are accelerating. And he says it's the same, he made the leap that it's the same sort of thing that has the moon going around the Earth and the Earth going around the sun. And he made that leap, and it was a very important one to make. And he introduced, the physics that describes the apple falling from the tree, as well as Artemis going around the moon. As we were talking about in Space Week, it's the same sort of Newtonian description of gravity. And so he would write down equations. I'm not going to belabor the mathematics here, but this is something that physics students will know all about, and it relates the force, which will designate in shorthand as an F, to the acceleration, and it gives an expression for the force that will apply on the Earth and for the moon, the rocket going around, the spacecraft going around the moon, and the moon going around the Earth, and so on and so forth. And it's a spectacularly successful description of the natural world. And it is truly remarkable, and it held sway for a long time, although the way in which it is expressed in a modern way, in a post-Newtonian way, if you like, is very different from Newton's original formalism. For one thing, it isn't in Latin, so you don't have to know Latin to understand this, but more importantly, the mathematics is different, but nonetheless, the conceptual basis of this way of looking at physics is unchanged. And so that's the sort of Newtonian prescription of this force that applies to the apple and the spacecraft and the celestial bodies in the solar system. And then, of course, Einstein came along. I'm actually leaping over an awful lot of physics that happened in between, but in 1905, Einstein came along and introduced his special theory of relativity. And, of course, the many things that he taught us, one is that space and time should be thought of as combined, not as totally separate things, not as something that's there as a sort of prior structure for space and then time which goes ticking and it's the same for everybody, but they're strongly interconnected, they're strongly related. And in particular, if you look at some physical phenomenon from a frame of reference that's moving, you get different measurements. There's no absolute time there that's involved. You really are talking about measurements. So this was terribly important, and we can have, and so they're combined, and also energy and momentum are combined too. And if we, there are many equations here, and I've written down the one that is allegedly the most famous equation in physics, E equals mc squared, although people are sometimes slightly mystified what the m means, even especially physicists, but I won't go there, I won't try and explain that. But basically it's this, not only are space and time combined, but two quantities you might have heard about either as physicists or as just as metaphors that's used in popular press or whatever, energy and momentum, they are also intercombined too. And so this equivalence here is what underlies things like, the nuclear power which happens in the sun and obviously in nuclear reactors and so on like that, and underlies an awful lot of modern, not so modern, century-old physics. This is sort of very central. But this is a special theory of relativity, and although I've shown here a cartoon that looks like it's got the Earth involved, it basically says that time is different. Basically, this is the so-called twin paradox, is that two twins, here a boy and a girl, one will go off on a rocket ship and then come back and be younger than the rather lazy brother who left behind, and And this is all perfectly reasonable expression of special relativity, albeit under rather extreme conditions. And you see this every day in the behavior of elementary particles. So that's the energy there, and that's related to matter. And this was sort of a revolution in physics. But even a larger revolution came from Einstein's general theory of relativity. And this introduced yet new further concepts. And this basically gave a new interpretation of what Newton had been saying. And instead of talking about a force exerted by the Earth on the apple, pulling it downwards, it said that the Earth provides a curvature of space-time. Now, these are just words. You actually have to wade you through for a certain amount of mathematics to get a proper understanding of that. But we think about this combined space and time, and we think about it like we might think about a sheet of rubber, for example, which is flexible and can have curvature in it. Then a sort of generalization of that idea to incorporate time is possible and quantitative, and it basically says that the amount of matter and energy that you've got tells you how much curvature you've got, and that's sort of shown almost figuratively here with the Earth bending this sort of sheet of rubber, if you like, and so this is embodied in a different formula, which I've written in shorthand here. I've written G equals 8 pi t. 8 you know about, pi whoops, wait a minute, that's not quite what I meant. That one. And then basically G is a measure, think of it just no more, of the amount of curvature that's there. And T is the amount of stuff that's there. And I say stuff rather than I say mass or matter, because it includes mass and matter, but it might include other things too, like, for example, radiation. But one example, anything that you can recognize that's not a vacuum is stuff for these purposes, and will contribute to the right-hand side of this equation. And getting this right and showing that it reduced in the appropriate limit to Newton's way of looking at things was the great accomplishment of relativity. And as so far as we can tell, at the level of sort of astronomy and classical physics and all the rest of it, despite large-scale experimentation and testing and assaults on its integrity and so on, it has survived all of this. And all of the alternatives that have been on the market, and they were not crazy things. These were things that was worth taking seriously. They have fallen by the wayside. That doesn't prove that there won't be something that will come along that might displace it at some level. That can still happen, and people are still thinking about this, but the options have been whittled down. For all intents and purposes, in astrophysics at least, we can take general relativity as a given. And there's many ways in which it could have failed and it hasn't. The big exception to this is when the other big revolution, which Einstein helped usher in, which is quantum mechanics, the physics of the very, very small, when that becomes unified with general relativity, at that point, all bets are off. And if anybody in the audience has a good idea how to make a quantum theory of gravity, you could see me afterwards and I'll help you with it, okay? Okay, so that's general relativity. Now, so let's go on to black holes. So within a year of Einstein in 1915 announcing his general theory, a German soldier, Karl Schwarzschild, shown here, wrote down a solution to these mathematical equations that, although he didn't recognize it as such, actually included a description of a black hole with an event horizon and all that. He was more concerned about the solar system, but subsequently it was realized that this actually had all the properties of a spherical, non-spinning black hole. And this idea had actually been anticipated by several people, including an English polymath called John Mitchell and also Laplace, who some of you may have heard of, that there might be a body that was so collapsed that not even light could would have the escape velocity from it. It wouldn't be able to get away from it. And that was sort of an important idea, but Schwarzschild really made this a sort of branch of mathematics. And, and you could say that on this basis, we concluded that black holes could exist, at least theoretically. And then this sort of idea sort of wandered in and out of fashion for the next sort of 40 or 50 years. But then several things happened in the 1960s. Firstly, Roy Kerr, shown here, discovered another solution to Einstein's equations, which described a spinning black hole. And it took a little while for the magnitude of what he had wrought as a piece of mathematics actually meant, just like with Schwarzschild, but it soon became clear that this was important. And then the properties of this solution to the spinning black hole described by general relativity were recognized by many people, including John Wheeler, shown here at the bottom left-hand corner, who he didn't actually coin the phrase black hole. It was an Australian journalist, but I think it was probably he invented it independently later, and then he certainly popularized it. And then other people got involved in exploring its mathematical properties, expressing them in physical language. And I'll call out two famous names, as Roger Penrose, you've already seen a picture of him, and Stephen Hawking, who needs no introduction. And there were many others around this who sort of, in 10 years, basically realized what the mathematical properties were. And it's about the physics expression, or the astronomical expression of this, that I'm really talking about now. And the bottom line of this is, as far as astronomy is concerned, it's just the mass and the spin of the black hole that's at play. They're the only things that matter. There are just two numbers, the mass, which is just a scale. Everything is just bigger by a factor of 2 if you take a black hole that's got twice the mass. And so it's just a scale there. But the spin does change the geometry and change the properties in ways that I'll explain. And that's all you need. They're very, very, very simple structures from the point of view of physics. Now, I say that from the point of view of astronomy, I meant to say. From the point of view of theoretical physics, well, theoretical physicists, if you know any, have highly febrile imaginations, and they can go off into other dimensions, they can add other fields, they can add lots and lots of other structure there. And for them, they can add charges and so on. All of this is good, clean fun. There's nothing wrong with it. They're interesting explorations, and particularly the interface with quantum mechanics has been extraordinarily fruitful. But as far as astronomy is concerned, which is what I'm talking about here tonight, all you need is the mass and the spin. The rest of it is unimportant. That's my contention. Okay, so what this basically means is that these black holes, instead of just being inert collectors of the week's garbage, they're really sources of energy. And they do this in two distinct ways. The first way is exhibited on the left-hand side. That shows a structure that's known as an accretion disk, and that's gas orbiting the black hole, and here illuminated so it can be seen. And because the rays of light are deflected by the gravitational field of the black hole, it looks distorted, it looks warped. So what was a flat ring, like the rings of Saturn, has this funny orange shape there. I won't guarantee it's orange, but it has that funny shape there. And that's the accretion disk orbiting the black hole. And so what you think about, if you take yesterday's garbage and then you orbit around the black hole, friction, and it's essentially a magnetic friction, causes that gas to spiral inwards. Sorry. Oh, like that. Okay, sorry. Is this a bit loud? I'm very undisciplined, I'm sorry. Okay, so maybe we should revert to this one, and I'll try and stand still. I think this is going to work. Can we revert to this one? Okay, is that all right? Can we, okay, all right, I'll try that. Okay, all right. So orbiting the black hole is this gas, and as it spirals inward, it releases its energy. It's like the apple that falls, an apple falls from the tree. it hits the ground. It's got what we call kinetic energy. It's got energy of motion, hits the ground, and that becomes a little bit hotter, releases that energy, may cause chemical reactions or whatever. And so the same sort of happens in an accretion disk, and you end up with a very efficient release of energy. In the terms of E equals mc squared, if you've got a mass m, you say there's a total energy mc squared associated with it, and up to 30 or 40% of that energy can be released from this black hole. It's very efficient. For nuclear reactions, it's less than 1% of that energy gets released. It's only a fraction of 1% of that energy that gets released. For chemical reactions, like something as innocuous as dynamite or TNT, then you get about 10 to the, then you get a fraction of a billionth of the mc squared out. So chemical reactions like dynamite give you nothing. Actually, if you want more energy, you should take a candy bar that's better than dynamite. It doesn't blow up as well, but it's got more energy. Anyway, so that's the first form of energy release. And then the second form of energy release that you have is associated with the spin of the black hole. And just like a spinning top or a spinning star can release its energy of rotation and will heat its surroundings, for example, as it slows down, so the same is true for a spinning black hole. Up to 30% of its mc squared energy is there for the taking. And the way that we now believe that this is taken is using magnetic fields, somewhat similar to the magnetic field that you associate with the Earth. And that is able, steadily and slowly, over cosmic time, to release the spin energy of a black hole. So the rotational energy is the second form of energy that's there for the taking. And so I'll say a bit more about how this happens and what we think is the expression of these two forms of energy release. So going on with a bit of the history here, on the left-hand side are two famous physicists and astrophysicists, Subramanian Chandrasekhar and it says Robert Oppenheimer, and they respectively were concerned with two types of star, called a white dwarf and a neutron star. I won't go into those. And they told us, they sort of, in retrospect, told us many important things there, but one of the things they told us was that there was a maximum mass that they could have before they would have to collapse, before the pull of gravity would exceed the possible resistance of pressure in these stars. And so there was a maximum mass, and it was a little bit, about 2 or 3 times the mass of the sun, and that was the maximum mass that you had available. And astronomers, meanwhile, were saying stars were going to end their lives with more mass than that. So from the point of view of stellar astronomers, black holes really must exist, historically. Now, going on to the early 1970s, then what was an epoch event was that there are black holes with masses of, say, 10 times the mass of the sun, as well as the very big ones in galactic nuclei. But the ones that are about 10 times the mass of the sun, they can form these accretion disks. They can be seen with X-ray telescopes, which are then being developed, and they were getting their supply of mass from a companion orbiting star, and that enabled astronomers to weigh them, to say how massive they were. And this particular one, known as Cygnus X1, it was satisfying its hunger by grabbing gas from the companion star. It was shining for the gratification of X-ray astronomers, and then the astronomers were then measuring its mass, and it was larger than the maximum mass of a white dwarf or a neutron star. Therefore, it had to be a black hole. So from the point of view of astronomers, black holes, an idea to which many astronomers were quite resistant at the time, do exist. They say we've shown that they do exist. And in retrospect, what others have been saying about the massive black holes in galactic nuclei, they also came to recognize that the evidence was there that the massive black holes also are present. Now, these black holes in galactic nuclei, they can be very, very heavy. Here is this famous one, M87, which was the source of the cat's eye image that we saw at the start. And that's that one there from the Event Horizon Telescope. This is the black hole, but it's been known about since Curtis in 1917 showed there was a structure called a jet. This isn't, of course, his images. They were much, much simpler than this. But he was able to see a jet that came out of the center of this galaxy called M87. And we now see it in X-rays, we see it in radio waves, we see it in gamma rays, and so on and so forth. It's seen, and it was measured by colleagues of mine, well, Sargent and Peter Young, in the 1970s, and they got about 5 billion, that's 1,000 million, solar times the mass of the sun, for the mass of this black hole. And the current estimate, the current measurement, the current measurement is just over 6 billion solar masses. So this, all of this was rather controversial at the time, but they got it right. You know, they got 5 rather than 6, so that was pretty good for astronomy. And so this is an enormously massive 6 billion solar masses, and the biggest ones for which we've got really good measurements are now about 20 billion times the mass of the sun. Now, I said that black holes can be these agencies for releasing energy. In 1963, the same time that the Kerr found his solution, and in fact announced at the same scientific conference, Martin Schmidt, shown here, found what was the first quasar, which was at the time just a point of light, and he showed that it was immensely luminous. And we now know these quasars are tiny regions no bigger than the size of the solar system, centered in the middle of distant galaxies, in this case cosmologically distant, and they can produce radiation using the combination of gravitational energy and rotational energy. They can produce radiation and be brighter than 1,000 galaxies. So they can outshine all those stars around them, just this little engine in the center, no bigger than the solar system. That is truly remarkable. Unsurprisingly, this is an idea that took a while to take root, because it was a radical interpretation, but it turns out to be, it's now commonplace and believed to be, known to be the case. So this is 3C273, the very first quasar. Now, black holes have other ways of releasing energy. Instead of having a steady flow of gas flowing through, throwing around the black hole, instead of having this steady flow of gas inwards, then they can also be quite dormant, like sleeping giants, waiting there, and then a star will come along, and that star, unsuspecting, I don't know whether there are any Greeks here, but think of Daedalus and Icarus and so on, things can go bad. And what happens in this case, the star is ripped apart by the gravitational force acting on it as it swings around in a very close approach to the black hole. So it's a star, a bit like those that are seen in the galactic center, that were seen by Reinhard Genzel and Andrea Ghez and their teams orbiting the black hole in our center. If one of those got very close to the black hole at our galactic center, it would be ripped apart by tidal forces, the same forces that the moon and the sun exert on the Mediterranean Sea that were clearly operational in Tel Aviv earlier this week, but much larger, so big that the waves were as big as the size of the Earth and then some, and were ripping off parts of the Earth. Imagine, the tidal force getting much larger, and that's what would happen to this star as it swung around a black hole. And this was an idea. This was actually a sort of cartoon of a cartoon that was made by Martin Rees, who was my colleague and advisor and teacher, and it's been one of the topics at the black hole. One of the big sort of topics at the Black Hole Conference is what was an idea that dormant or sleeping giant black holes there's a single star that will swing by and be ripped apart, and then that'll provide a gas supply which can shine as X-rays, as optical radiation, and probably a lot more besides. And we can see it with our telescopes and learn a lot about the black holes and how gas behaves in its vicinity. This is called a tidal disruption event. There's a movie here. I have no idea whether this is going to work. I hope. Are we connected to? I meant to say, are we connected to the web? Yes, it could be. Yes, I think. I thought we're seeing. That's why I wanted to use my. Yeah. So I have some movies here. I thought we were. Can we be connected to the web? Sorry about this. This is bad planning on my part. Let's see if we can get up there.
Okay.
Yeah, go ahead. Does that work?
Yes, yes.
Now I need to get back to
Earth.
Back to Earth. Thank you.
You need YouTube?
This was YouTube, yes. I think that was a YouTube. Okay, we've got something different up here, yeah. But I've lost it here.
Okay.
Yeah, I've got a cup of coffee here, so. Sorry about this interlude. Shall I try and advance the slides? Or advance them this way, maybe. No, it's not advancing here. So sorry about this. Well, there you go. So no, there's nothing happening here. Maybe we can. Okay, we've got. Yeah, that's the one, but we want to do it in full screen, I think. Need to put it in full screen and see if we can. That one. Okay, now let's see. Now let's see if we can do it here. there we go. There we go. Okay. Oh, thank you very much. Thank you. So here's an extreme version of the distorted black hole. The actual this actually was made, I think, by a team in London. I met them once, and I said this looks like the London Underground, but this is sort of there's a certain amount of space art here, of course, but it gives some idea, and you'll see in this short clip of what is envisaged to happen to a star as it gets strongly distorted, as it swings around like that, making all of this gas ripped apart and then falling into the black hole, radiating as it goes. And so that's what we see. And then what you also see here is something that happens occasionally, is that you make these what are called jets, which are these sort of two linear outflows, and we'll see more examples of these shortly. And I'm not quite sure where this movie is going. Oh, there's the jet there. These occasionally happens in these so-called tidal disruption events, and there's a Jovian thunderbolt. Okay, so let's move on. Now, I'm not quite sure how I get back onto the... Sorry? I did the transition slide. That didn't happen. Okay, now maybe that'll go, and then I could... Yeah, here we go. Okay, so, all right. So this is the black hole at the center of our galaxy, and these are the stars I mentioned that are orbiting them, a little bit like the solar system. And the one that's at the center of our galaxy is very sleepy. It's not like one of those quasars, 1,000 times brighter than the host galaxy.
Somebody asked what's the time scale?
Time scale for the previous movie. Okay, very good question, and I'll do more questions afterwards, but very good question. These tidal disruption events, they typically go on for months to years. So there's some happen faster than that, but that's a sort of typical time scale for the whole show. So it's a good question. We'll come back to that in a moment. So let's see what we do with this one. So these are the stars orbiting in our galaxy, and if you're feeling a little ashamed of the black hole in our galaxy, and you wish we were a quasar, do not be ashamed. You would not like to live next to a quasar. There we go. Yeah. So this is, again, another graphic. And this is imagining zooming in through all of the dust and the gas. You have to look in infrared wavelengths, because optical wavelengths it's too dusty. You can't see anything. But infrared you can. And this is a tour de force of measuring, it's doing like flying planets around the night sky, but stars orbiting the black hole in our galactic center, and shortly you'll see them. And all of this has been measured, and not only has it weighed the black hole, it has verified that Einstein's relativity is working just fine in this environment. So shortly you'll see, this is just obviously a graphic here, but it gives you some idea of the going down to something much smaller than the solar system at the center of our galaxy. And then you can see these stars moving around. These are observations. You actually see them moving around, and you can learn a lot from watching these stars orbit an invisible black hole at the center of our galaxies. And so let's see. And then here we can, let's just, I think this has got, this shows you as time. These are actual observations. We're tracking these particular stars, and this is the date here, orbiting, and these are different stars, and you can do all this exquisite work with observational astronomy. It's remarkable. I can't begin to explain to you the technical challenges that had to be overcome to pull this off. Okay, let's move on maybe. Okay, we're almost there. Okay, there we go. I think that's it. So there's a magic that I have to use, is it? There we go. Got it. I'm learning. I'm a slow learner, but I got there. Okay, so it's mere 4 million solar masses, the one in our galaxy. Now, black holes cry when they are born. Does that sound familiar? here's a supernova happened in a nearby, very nearby galaxy. It's essentially within our galaxy, and we used to think about it as a sort of little thing. It turns out it's 10 times as, okay, thank you, I've learned, it's 10 times as heavy as we used to think it was. It's called the Large Magellanic Cloud, and in 1987, a supernova explosion went off in it, and this is what it produced a little bit later, this spectacular art show. This is observation, not some cartoon, and I won't explain what's going on unless anybody asks me. And then these black holes, when they are, this is almost certainly the birth of a black hole. And there are structures called gamma ray bursts, which represent the birth of black holes, which we can see by one of two different routes, either through the supernova like this one in the Large Magellanic Cloud, or from two neutron stars combining together and making gravitational radiation when they're merging together. And that's two different ways of making black holes, and they create this burst of gamma rays. And that, I think, I always say is the birth cry of a black hole. So these are gamma ray bursts, and we see those across the universes. And I would say that black holes also have magnetic personalities. Remember I said that black holes can have rotational or spin energy, and this can be accessed and extracted using magnetic field, rather like the magnetic field that's associated with the Earth. And here's a computer calculation of a black hole with magnetic field lines with the arrows on them going through the black hole, and that's extracting energy from them, and that we believe is the source of the energy or the power for the jets. And I showed you some jets in that cartoon for the tidal disruption event. It's a much more common thing in astrophysics. In the case of this famous galaxy M87, the one with the cat's eye shown there, we can see jets coming out of this on larger and larger scales, and these jets go way out, eventually will go way outside the galaxy and will keep warm and prevent further infall of the gas surrounding that galaxy. So they have a huge environmental impact, and these jets are basically powered, we think, by magnetic field lines attached to the spinning black hole in the center of that galaxy. And the black hole itself is rather relatively feeble to what it was in the past. Today, it is perhaps 1/10,000,000th or so of the power that it had when it was in its prime. In its prime, it would have been as bright as the brightest stars we can see today, this black hole in a distant galaxy. So if it had behaved, it would have been a quasar in the past, and it would have been that as bright as the very brightest stars. So our ancestors would have enjoyed seeing that, maybe. And these so-called jets, these structures, are making the highest energy gamma rays, possibly the very highest energy neutrinos that I mentioned. This is all sort of work in progress, as it were. There's a reasonably good hypothesis that they are making the very highest energy neutrinos, which we're seeing using telescopes. And then the ultra-high energy cosmic rays. Remember I said the cosmic rays with energies as much as a well-hit tennis ball. One of the best candidate sources for these cosmic rays are jets in galaxies like the one coming out of the black hole in the galaxy M87. So again, these can be enormously productive in this regard. Now if we go on, these jets themselves as structures, they are everywhere. And some of these are associated with black holes. Here is a map of a tiny bit of the sky seen with a radio telescope in South Africa called Meerkat. And it's a very successful telescope in South Africa, and it has just made a small patch of the sky. And if you multiply this up by the whole sky, there are 2 billion sources over the sky, and half of those we think are jets coming out of black holes across the universe, seeing right across the universe. And whatever we see from our galaxy is about 10,000 times too faint to be seen in this. If it were at the other side of the universe, we would never see it. So there's lots and lots of jets out there. Here, as I mentioned, is a candidate source for the neutrinos, not proven yet, but something like this is probably going on. Here's actually a neutron star. I mentioned those earlier. That makes jets. Here's down here, I think you say, here is a protostar, not even a neutron star, just a star in formation. This is one of the most famous images in recent astronomy, made by the ALMA telescope. That makes jets. Here's a black hole on the stellar scale with about 20 times the mass of the sun in a nearby binary star in our galaxy. That makes jets. And it's a black hole then. It does lots of other tricks. It dances all the time. It's quite remarkable. Here's a tidal disruption event I mentioned. Occasionally I said they can make jets, as in that cartoon. Here's an observation that exhibits it. And then I said the merging neutron stars, they can make, they have, not only do they make the birth cries of black holes, they can create jets from day one that squirt out in opposite directions. And here's the 2 merging neutron stars that were observed 5 years ago, nearly 5 years ago, over 5 years ago, sorry, and those 2 make jets. So this extraction of spin energy, as well as the extraction of gravitational energy, is, I think, very much now seen to be a commonplace thing. So are the common mechanisms at work? I said that black holes can change their environment. Here's a nearby so-called cluster of galaxies. It's about 1,000 of galaxies that are congregated together. It's rather like what happens in this M87 galaxy, but a bit further away, about 2.5 times, about 3 times further away. And what we see here is the hot gas observed with the X-rays. The black hole is in the center of a galaxy located there. Then on the very much larger scale, this thing that looks like a skull. I like showing this at Halloween, for those of you know what Halloween is. And it sort of kind of looks like that. But what these things actually are huge bubbles that are blown by the jets coming out of the center of that, the black hole at the center of that galaxy, blowing these bubbles, and they're floating upwards in the surrounding gas, the gas surrounding this giant galaxy. So, not surprisingly, this has a huge environmental impact, and it mediates and promotes the formation of galaxies and their growth over cosmic time. So it's an enormous impact on how galaxies and the stars that are within them actually came to be. And so in practice, these jets almost certainly are the part of the feedback that stops galaxies from galaxy growth from going away and moderates it. As I said, you can have binary black holes. You can have black holes just like stars can have companions. They can have dance partners. Here are 2 seen by radio astronomers. Here we have 2 black holes in orbit about each other. There's another pair in orbit about each other. In this case, is a rather famous case because they both make jets. So we can see, not in real time, but we can see as a single snapshot how those jets behave as in 2 black holes essentially orbiting each other. And one of the things I think I can confidently say, we're going to see a lot more of this in the years ahead. So black holes are not just solitary partners, they really are social animals. They want to find partners. And so, where there are various ways that we can find this, and we think we are going to start seeing them. So here we go. And here's something that I was involved in recently. This was a positive binary black hole where what we think we are looking at is two jets now in very much close orbit, where the orbital period is, in our frame of reference, 2.5 years. And it was actually discovered by an undergraduate, Sandra O'Neill, and there's her advisor, Tony Reedhead, there. And I was sort of dragged into this too, and very, very willingly, to help interpret it. And what you can see is sort of evidence of a on there, and then off in between, but a coherent period, which we think is two orbiting black holes, making jets. And what's important about these jets, if you imagine, I'm dressed for the part, if you imagine I'm a black hole with a jet like that coming towards you, because of special relativity, if the jet is coming towards you like that, moving at nearly the speed of light, that will be bright. So the jet that is pointed at you is bright. This is not paranoia, this is physics. So it comes towards you, and the jet is very bright, and that is what we think we're looking at here. And here's another sort of media production that's for this, and not quite sure how this is going to come through. There's a certain amount of license that one needs in doing this, and as I say, they travel at nearly the speed of light, and then the two of them in orbit about each other. As I say, they're brighter as they come towards us, they're brightened, and so you can see some, there's a lot of music. I suppress the music, so you can see, and these oscillations, and you've got 45 years of radio observations, you were able to see this period, and what you see is there's two black holes there in orbit about each other every 2.5 years or so, and one of them has a jet, and that's what you're looking at. So this was, again, the sort of result of this sort of social interaction, if you like, of the black hole with another black hole, and there are many other ways in which they can interact in this way, and they're sparring closer together, and I think we can probably have enough of that. So, oh, it's almost come to the end. I'll just be patient. That's right, and so now, okay, so it's a 2-year period, and so finally, if I advance like this, can we? Okay, wait a minute, so what happened then? I think it's my last slide coming up. Sorry about all this. Maybe problems. Okay, so that goes forward. Okay, this is the one I think we want. Okay, and this is what happens at the end of this devil's dance. Is we've got the two black holes coming together, which on the stellar scale was seen in gravitational waves by LIGO. This was the sort of first Nobel Prize, if you like. And you get the gravitational waves that are seen on the right-hand side from two detectors in the United States. And then this obviously is an image, but this is what background stars would look like as a graphic, and as those two black holes come together and merge, and then they shake around a little bit and then settle down. That's the end of the devil's dance, and that was what was seen in gravitational radiation. And so maybe we can get to the end of this. And if you, in terms of power, I said that the quasars were 1,000 galaxies, or 1 trillion stars, if you like, 10 trillion stars. This is, in terms of power, is 1 trillion quasars. So gravitational radiation, this is 1 trillion quasars. So this is a truly impressive cosmic event, And black holes should be proud of it. And they are, trust me. Okay, so I hope in this talk I've been able to persuade you of three propositions. One is that black holes are very much not dead inert structures, they're very much alive. Secondly, they thrive, they grow by accreting gas, by bringing together gas. And thirdly, they survive just fine. So let's hope the same for us. At any rate, thank you very much indeed. I'll try and hold this.
Questions for the speaker?
Yeah.
You could use that one. Okay.
Are all black holes post-Big Bang events, or there might have been black holes that just are outcome of the Big Bang itself?
A very interesting question. I think most of us would, there have been people who said, well, they tunneled through from an earlier universe or some such. I think that's incredible. But it is possible that some of the stellar black holes, including especially the nearly 100 pairs of black holes that are seen now by LIGO, it is possible that some of those came from an early phase of the universe when it was much younger. These are they're sometimes called primordial. It is less credible, but not entirely ruled out, that they were made much earlier in our evolving universe. But most astronomers, including the ones who were present at the symposium on Wednesday who discussed this a bit, by and large think they are made comparatively recently as a result of a lot of changing partners and so on that goes on inside star clusters, especially globular clusters, possibly other types of star clusters, but especially the so-called globular clusters. And there's a sort of even more rapid social interaction that goes on that would impress a contemporary teenager, and that is, they think, is the genesis of these black holes. But it's possible that some of them come from earlier stages in the universe, but I think most of us would bet against it now, based on more recent evidence.
Okay, your permission, I would like to ask you a question. Well, you mentioned those stars rotates in the center of the galaxy around the black hole.
Yes.
So my question is, what occurs or what are the consequences to those stars while spinning so in this velocity, so fast and so rapid? What are the consequences to those stars? What happened to them while rushing so fast?
Understood. Those stars did not go close enough to the black hole to have too much to happen to them. Now, there's one exception to that, which the aficionados is an event known as G2, and it is possible that that was a very large star called a red giant star, and there may be gas that was ripped, it may have got close enough to rip the gas off that. That is possible, okay? But most of them were far enough out that they were not destroyed, whereas the tidal disruption events had them destroyed. No, they behave essentially like point masses, like the planets in our solar system. So as far as we can tell, they follow the same orbits as a point would follow, point mass would follow, like the planets in our solar system.
Thank you for your lecture. I have two questions. The first one is regarding the nebula we saw. Is a black hole exist in each nebula?
Each galaxy, I think most of them, I think, is what we would say now. And I'm going to give you a rather local parochial answer, and that is I remember I introduced the Large Magellanic Cloud, which we used to say had a mass of 1% of the mass of our galaxy. And recent measurements have stunned at least me, and I think many others, to show that its actual mass was 10% of the mass of our galaxy. So that you'd expect to see a black hole in the center of it. And astronomers have been looking for it, and they haven't found it yet. So that's a possible counterexample. My guess is they will find it.
Thank you.
But it's also possible that the black holes are thrown out of the center. They were there once and were thrown out. And I'm going to use a slightly risque metaphor here in this social interactions theme. If we have two black holes in one of these binary systems, like the ones I showed in the movie, going around each other like that, guess what might happen if a third one comes in? That's an socially unstable situation, and also dynamically unstable situation, and the whole lot can go away. That's one possible mechanism.
Thank you. The second question is regarding white holes.
White holes, yes. Okay, white holes are lovely. They are time-reverse black holes. Science fiction writers like them. And I'm sorry, I don't believe in them. One of my colleagues long ago showed that if you had a white hole, which is a solution to equations, and you make a little bit of a perturbation to it, you hit it, you make a little tweak to it, it collapses into a black hole. So I think these white holes are figments of the creative mind, but not realities. Now, I can find you a few people with whom you can correspond about white holes, and I wish you well at this.
I would like to ask a question. You mentioned quasars earlier, suck large amounts of mass around them. Now, to my knowledge, it is very hard to actually fall into a black hole. So, during the friction, how does the quasar not run out of fuel? Like, doesn't it turn into heavy elements?
It is not hard to fall into a black hole. It's hard not to fall into a black hole. And I think you might be referring to what is a serious so-called paradox which confused very good physicists during the 1940s, and many, but not all, during the 1940s and 50s. Let me take, what am I going to take? I'm looking for anything. All right, I'll take this. Okay, I am a black hole. Okay, you are observing this. If you observe this, which might be some unwitting graduate student or whatever you've sent on this path, falling in like this, from your vantage point, you will not see it cross the event horizon. What you will see is your graduate student who's pathetically sending out signals saying, "Save me," in Morse code or something. The intervals between the signals will get longer and longer, the light will get dimmer and dimmer, and you'll get the last photon in a finite time. However, in a mathematical sense, you will not appear to have crossed the horizon. But don't tell that to the hapless graduate student, because by the clock on their wrist, they have crossed the event horizon and are on their way to their doom. Okay? So that's maybe the paradox to which you are referring.
Any more questions? Oops, sorry. I've optimized the route.
Yes, I would like to ask you about the research you showed us, a graph of the two revolving black holes. At the end of it, it's a perfect sine wave, but like at the two early stages, it's acting very weird. At the first stage, its amplitude is very big, and at the second, it's like very long sine wave. Can you elaborate on that?
Happily, yes. And it's for this reason that not even the authors of this research, which I'm a sort of minor player, are totally convinced by the story. So this is, work in progress, but I'll come to that in a moment. What you're looking at is not the black hole. You're looking at something that it creates as a secondary feature. So I'm the black hole. I've got a disk of gas around me. I'm spinning like that, and then I'm making a pair of jets like that. Now that's a lot of engineering that happens between the black hole with geometry, but then the gas and the jets, there's a lot of engineering that will happen. And if you then modulate that by my motion around another black hole, that won't change. That's essentially geometry, that's just orbital mechanics. That should be a very good clock. But the making of the jets is intermittent. And that's what we think is going on. Now if we come back, I'll get back to my microphone, here we go. If we then say, well, what's the test of this? Watch this space. We're going to be observing that, and we've got other ones like this. We're going to be observing them in the years ahead. And if they still keep up that sinusoid, then I think everyone will be persuaded. If they don't, then the jury will still be out.
But do you think the weird behavior will repeat itself, or is it because they came together?
No, they're not coming together. It's going to be nearly 1 million years before those two black holes.
No, I don't mean collapsing. I mean start going in orbit.
We're not seeing any stars from those. Those are massive black holes in the nuclei of galaxies. So we're not seeing any stars there. We're seeing, just looking at massive black holes orbiting each other.
A question regarding energy. You described all those black holes and their relations with each other and the galaxies. Is energy infinite? When a black hole is born and then it loses its energy, it releases via jets and magnetic fields and other stuff. Where does all that energy goes? Does it return to other planets or other black holes, or is it lost forever, or is it contained?
Okay, I'm going to give you a slightly long didactic answer. Newton, as I emphasized, was all into forces, pulling and pushing, and force is equal to acceleration times the mass and stuff like that. And that's a very mechanical engineering type way of thinking about things, and it's been very, very, very useful. Physics, following Leibniz actually, who basically introduced the idea, was Weber, introduced a notion of a quantity called energy, which is originally just the energy of motion. And for a long while, physicists were honestly confused about it, but they got it sorted out eventually. And there were huge debates between the Newtonians and the others. And the others turned out to be essentially correct. And then as physics developed over the 18th and 19th and 20th centuries, the center of focus became energy more than forces. And energy really was it wasn't just a fashion statement. It was because this is the useful way to think about physics, was in terms of energy. And quantum mechanics can be expressed at some level in terms of forces, but overwhelmingly the development is one expressed in terms of energy. Then there was the principle of the conservation of energy. You can change energy from one form to another. I can drop the apple on the floor. There's gravitational energy, which becomes kinetic energy, which becomes heat, mechanical energy from a vibrating apple, say, and then heat energy and so on. And then the apple rots, and so chemical energy is released. and so on and so forth. We've got energy in the sun. Now, the physicists have had a principle which goes back to, actually, there's a woman called Emily de Châtelet who sort of got the idea in many regards, was one of the first people who did this, that energy is conserved. And the history of physics has been one successive failure of the principle of conservation of energy. But every time it has been failed, it has been recovered by introducing a new form of energy. I'm oversimplifying slightly, but it's been recovered by introducing a new form of energy. And people doing nuclear physics in the 20th century, serious and solemn people, said, well, maybe energy is not conserved here. And then they rethought about how they were doing it and said, no, if we change it in this way or that way, we've got a nice, tidy, working formalism which conserves energy. And time again, energy has been conserved. So when we get some energy released, it's come at the expense of something. So, for example, if we have gas orbiting the black hole, as it spirals inward under friction, the gas loses energy, it goes into heat, which then goes into radiation for the gratification of optical astronomers or whatever, looking at this from a distant planet. Energy is conserved, and you might say, well, what happens to the black hole itself? Well, some of that mass will go in, and the way that it goes in will make the black hole's mass and its E equals mc squared energy larger. And that E equals mc squared energy will be part of your big conservation of energy equation, and the sums all work out. The balance sheet works out. At the end of the day, when you've put everything in place, energy is conserved, and what you lose there is gain there. So that's a slightly longer question you asked for, but I think it's an important point to make. And so there's as a practical matter, there's never been any cheating the principle of conservation of energy, however much people may try and persuade you otherwise.
Hi, so I'm curious, so if the event horizon of the black hole defines like time stopping, basically, and the mass of the black hole, from what I understand, is supposed to be infinite, and it stops time, what does the process, what happens when a black hole dies? How does it actually burn out? Because if it stops time in and of itself, then how does that function?
Well, I'm not sure that time. I'm not sure that time stops. What I can do, okay, let me think about this. I can just have a piece of string like that, and it can. Let's take maybe something like this. I can have something. Whoops. Okay, all right. I'm clearly not set up for. Let's have something like this. Take my two thumbs. I can have two measures of the distance between my two thumbs. I can take a ruler between them and say it's so many centimeters or whatever. Or I can measure the distance along the wire here. And there'll be two different measures. So my measurement of distance depends on what we would say in physics, the coordinate system, the set of coordinates we set up. And that's a trivial example, but I can say that I've got different ways of measuring distance between 2 points in space. Now generalized to space-time, it's just the same there. I've got different ways of measuring space, different ways of measuring time, and different measures of distance. So when you say time is infinite or something like that, you've got to do this in the context of a particular coordinate system. Okay? So what happens around a black hole should really be thought of in terms of the outcome of what Einstein introduced the idea of Gedanken or thought experiments. And so he said, imagine the Bern trains traveling close to the speed of light or something like that. They don't travel at the speed of light, but you could imagine it and say, what will happen next? So you can play those games very much in the context of black holes. And many of the wonderful semi-popular textbooks written about black holes, including one by my colleague Kip Thorne, which is one of the best, sort of exhibit these thought experiments and give you the answers to those questions. Nobody's actually performing the experiments, but we do know how to calculate them. And that's the right way to think about crossing the event horizon. You ask, well, what does this graduate student see on her wristwatch as she goes through the horizon? And that's a thought experiment you can give a clean answer to and say what the ticking time will give you. And you can say, well, what does somebody looking from the outside see? And that'll be something different. And in that sense, it all makes sense, and it all hangs together as a logical structure. That's not quite, I think, the answer you might be looking for, but that's the way I would express it. Oh, the end, sorry, that was the other question. Thank you, yes, I forgot that. The end, black holes, okay, I'm talking here about astronomical classical black holes. All they do is they eat one way or another, and by the right measure, they put on weight. Sound familiar? However, now, it's by the right measure. If we measure mass in one way, it includes the rotational energy of the spinning black hole. That, see if I can slow down, and I can release that energy, but what we might call the irreducible mass, there's a measure of mass, and they eat and they just get bigger and bigger and bigger. Okay? Now, the exception to that is a tiny, tiny, tiny black hole, no bigger than mass than a terrestrial mountain, that can lose energy through a process called Hawking radiation, which is quantum mechanical. They may exist in the universe, and many, including me actually long ago, had been part of looking for these black holes. We have not found any evidence that they exist as yet, except in the minds of theoretical physicists like the late Stephen Hawking. And they've been wonderful sort of testing grounds, if you like, for theories of physics. And people are still asking questions about thought experiments, if you like, about these so-called tiny baby black holes. And they can lose mass. But the classical ones, the ones we're actually observing with our telescopes, no way, they just keep on growing. So all that happens is they're not fed, and they just sit there waiting for their next meal. And as the universe gets older and wiser and more tenuous, those meals are fewer and fewer between, and they just have to live off a meager diet of the occasional passing star.
So let's thank Professor Roger Blandford again for a wonderful talk.
Thank you very much. Thank you.
And thank you everyone for coming here tonight.